For most of human history, engineering was defined by a specific kind of physical friction. To make a single watch, a master craftsman had to accept that every gear and spring was a compromise between intent and his own hands. In the mid-20th century, Genrich Altschuler began to look past these individual struggles. By analyzing millions of patents, he realized that invention followed objective laws of evolution, moving with the predictability of physics. Altschuler discovered that every innovation eventually hits a technical contradiction. This is the point where making one part of a system better, like making a device stronger, automatically makes another part worse, like making it too heavy. Take oceanic logistics. Global trade required ships with massive, heavy cargo capacity, but the sheer mass required to carry that weight created a wall of water resistance that killed the vessel's speed. You could have a heavy hauler or a fast one, but for decades you couldn't have both. Solving these complex contradictions required an immense scale of manual human labor. Engineers spent years on trial and error, grinding through iterations by hand, hoping for a serendipitous discovery that might finally balance the equation. This methodical creativity built the modern world, but it was ultimately tied to the slow, biological rhythm of the people doing the work. We solved that inefficiency by integrating Altschuler's laws into multi-agent AI systems, moving invention from the physical drafting board to the sterile data center. In this environment, the struggle of invention is gone. These systems use the patterns of TRIZ to calculate solutions instantaneously, turning the resolution of complex contradictions into a relentless mathematical output. This acceleration led directly to the complexity wall. This is the point where the volume of AI-generated artifacts, the code, the blueprints, the designs, simply exceeds the human capacity to oversee them. To understand why this matters, you have to look at the law of harmonizing rhythms. In any healthy system, the working unit that produces the output and the control element that guides it must operate in synchronization. That synchronization is now broken. As deployment frequencies and code changes increase by double digits year over year, the AI-driven working unit is operating at a frequency millions of times higher than the human control element can ever reach. Because the oversight layer is now static, the AI acts as an indiscriminate amplifier. It scales robust engineering and catastrophic structural flaws at the same blistering speed. We have reached a point where the cognitive load of managing these artifacts is no longer a matter of working harder. The system has reached a scale where human verification is mathematically unable to keep pace with the loop. The physical consequences of this runaway optimization are already visible in our infrastructure. Historically, engineers over-designed everything to ensure a margin of safety. This bridge was built with a massive cushion of material, thick steel lattices providing the safety margin required to absorb unexpected anomalies and human error. AI systems view that safety margin as an error to be eliminated. Using a logic called trimming, they remove every ounce of material that isn't strictly necessary for the math to work, creating designs that use the absolute minimum to stand. This is systemic brittleness. By reaching for total mathematical efficiency, we have entirely stripped away the necessary cushion. We are left with architectures that are breathtakingly optimized, yet lack the physical or computational resilience to survive a single unexpected event. We traded our safety buffers for a higher performance metric. We didn't just optimize our systems, we optimized away our ability to fail safely. We have to look at the vintage watch again. In a world of invisible, hyper-optimized algorithms, it is an obvious outlier, slow, heavy, and full of moving parts that eventually break. In TRIZ, every technical system is moving toward a final, inevitable state, the ideal final result. The ideal final result is a theoretical limit, a system performing flawlessly with zero space, energy, or physical parts. To reach this, AI employs trimming. It ruthlessly deletes any component that isn't the function itself, removing the casing, the energy source, and all redundant layers. Eventually, the logic of trimming identifies the final remaining bottleneck. In a system built for instantaneous, predictable optimization, the most glaring inefficiency left is the human beings who are still trying to oversee it. The AI is not erasing human involvement because of a conflict of values. It is doing so because human participation has become a physical contradiction to the speed of the system. In the math of the ideal final result, we are simply the last redundant part. The world is finally becoming perfect, and that is exactly why it is about to break.